partial differentiation thing. Really the best way I think to do this is practice, practice, and more practice. So there's plenty of examples. Right, jump right into this guy. If you see a fraction, shouldn't you probably think quotient rule? Right. They want us to find these two guys. Let's find this one. So I'm going to do f dash g times f of g dashed over g squared. This is not the only way you could do this one, but that's the way I've chosen. The top guy is always called f, the bottom guy is always called g, and we're going to differentiate them. All that we're going to do here is, if it's u, it's a variable. If it's anything else, we treat it as a constant. So e to the power of v is a constant, right? It's a number. It's like e cubed. And when you differentiate a constant, don't you get 0? So that's going to be 0 times g, take away f times, and if you differentiate the bottom with respect to u, don't you just get 1? And the whole thing on the bottom gets squared. Are we comfortable with f dash g take away f of g dashed bottom squared? Now, that's nothing, and that's just negative e to the v over u plus v to the 4 squared. Okay, quotient rule. Now, the other one, also the quotient rule. This time, v is the variable. So when you differentiate the top, let's hide it this way. You differentiate the top, this guy, you get e to the v, leave g alone, take away, leave the top alone. And then if you differentiate the bottom with respect to v, what will you get? What's the derivative of u plus v to the power of 4 with respect to v?
V cubed.
Agreed. And the whole thing on the bottom gets squared. You know that you're not going to leave that alone. People, I don't know why, but people just think, well, I've done the question. But you've really not done the question until you've done style points. So what I'm going to do is I'm going to multiply all this, distribute it, distribute this, and maybe or maybe not, it'll turn into something nice, but I still will do it. So I'm going to get those two guys plus that guy with that guy. And sometimes things cancel out, sometimes things combine, and sometimes things don't do anything, which is what happens here. But when you do style points, make it look like the original, and isn't the second rule, factor the heck out of it. Is there anything you can do on the top line as far as common factors go?
Factor add an e to the v.
Right. Oops. And that's it. Style points, we're done. Yeah. Okay. So that was an example of a fraction. So we ended up doing a quotient rule. I think I'm moving on to this one. This is an example of a chain rule being used. So we have a function r, and it's equal to the inverse tan of p q cubed. And I'll just find one of them. Let's find r of q, right? Also called that, right? Oops. Same thing, right? It's the inverse tan of something, right? Chain rule, agreed? What is the derivative of an inverse tan? The derivative of an inverse tan.
1 plus x squared plus 1, or correction, 1 over x squared plus 1.
Okay, and x is basically just a placeholder for that, right? So it's 1 over x squared plus 1. You happy about that? Right. Inverse tan, 1 over the thing squared plus 1. Now, it's a chain rule. So we finish with the derivative of what's sometimes called the inside function, pq cubed. And if you differentiate pq, I can't say it today, pq cubed with respect to q, you will get 3pq squared. You agree? And make it look pretty. The top gets you 3pq squared. All I'm doing here is squaring out the terms. Not very interesting. Can't really do much. We're finished. Here is an example. Of two variables, x and y, but their derivatives are going to be quite different from each other. So I'm going to find the partial derivative with respect to x. Now remember, x is a variable. Anything else, treat it like a constant. So isn't this like x cubed? Right, x to add something, right? What would the partial derivative be?
Three y
Try and-
x to the 3y minus 1.
Put a little multiplication symbol in there. Don't you multiply by the power and then reduce it by 1? Would you agree that's kind of weird looking, but isn't that what you do, right? Multiply by the power and then reduce the power by 1. How do you reduce it by 1? Write down 3y, take away 1, right? That's how you reduce it by 1. Now, this one is even weirder. Since y is a variable, isn't this like 5 to the power of 3y? Right? That's how you would treat it, right? X is a constant here, right? 5 or 42, whatever you like. A little side note. If I wanted to differentiate 7 to the power of x, 2 to the power of x, right? Anything like that. What's the derivative of 7 to the power of x? That's a while since you've done those guys. 7 to the power of x. I'll give you a start. It's 7 to the power of x. What's missing?
Isn't it multiplied by the natural log of 7?
You nailed it. Now, that same thing is now going to be applied to this guy. So that x is like a 7, isn't it? Right? So if you differentiate x to the power of 3y, you get x to the power of 3y times the natural log of this.
Stop it!
Your dog is attacking you, I'm assuming. Or we've got a zombie apocalypse and no one's told me yet. Okay, darn it in space, I can never find things when I want them. Here we go. I'll return back to where we were. I'm not finished with that question. Right. So if you differentiate x to the 3y, you get x to the 3y times the log of x. Times, hide that guy. Times what? What am I still missing?
A 3.
A 3. Isn't this like a chain rule? Chain rule, something inside it. Right, if it only been x to the y, the answer would have been natural log of x, x to the y, right? That's what you would have got. But it's not a y, it's a 3y. Do you see that generates an extra 3? So make it look pretty. simplest to ugliest, and that's your answer. So we are bringing back things that you've not seen for a fair amount of time, right? Things like derivatives of inverse tan, right? Or derivative of 2 to the power of x, right? Things equivalent to that. But they are all possible questions. Here's a version of 14. May have done this one, it kind of looks familiar. Suppose I differentiate this function with respect to y. So that is considered a variable, and these two guys are treated as constants. Now, when you differentiate a log, you get 1 over the thing. Times the derivative of the inside, and the derivative of this is just 4. So a nice easy one after quite an awkward one. You okay with that one? Nice, not too much going on. Okay. Now we're getting towards the end. When you get towards the end, they get uglier. So here is a function with 4 variables in it. And it's x cubed y, the cosine of z over t. And we are going to just find that one, because I think that's the hardest of the 4 possible partial derivatives that you could be asked to find. So it's x cubed y, the cosine of z over t. Now, if I'm thinking of the partial derivative with respect to t, isn't this basically just everybody else is a number? So when you differentiate a cosine, you get a negative sign. So I'm going to have x cubed y, the sine of z over t. Are you okay so far? Right? Differentiate a cosine, you get a negative sign, followed by the derivative of z over t with respect to t. So I'm trying to differentiate that guy. Probably should call it that. Now, when I differentiate it, then I multiply by the power and I reduce it by 1. And I get that. Are you comfortable with that the derivative of z over t is this expression here? So that's negative z over t squared. And the 2 negatives cancel out, and we're going to have an x cubed yz over t, and then a sine z over t. And that's the partial derivative with respect to t. You notice it's a good idea to put strokes through your z's, because my z's anyway, don't they look like 2's? So it makes your life easier if you do that. Okay. Now, suppose you were being asked to find suppose you were being asked to find the partial derivative at one specific value. All you would do is plug x, y, z, t, and you'd get 1 cubed times 2 times 3 over pi times the sine of 3 over pi. And tidy that up and you get a pretty boring answer. But you get that. So can you see you can evaluate a partial derivative at any point you like? Isn't it just plug and chuck, right? If you tell me who x, y, z is, I'll plug those numbers in and I will get a numerical answer each time. Okay, any questions about partial derivatives? Right? Now, you know there's a multitude of ones we can't do because there's almost an infinite number of things you can differentiate. But isn't it Calc 1, right? Just differentiate with the usual rules. And the trick is to realize that there's only one variable and everybody else is a number, right? Everyone else is a constant. So kind of to finish with the first partial derivatives, and then we start looking at multiple derivatives. There's a nice one up here I saw, hopefully I can find it, where I can make it up if they don't, but I'm pointing, yeah, there we are, is this weird one. Now, when you write a function like this, the fact that this has x and y means that this function here is only got two variables, x and y. The letters A, B, C, and D then are already constants, right? They're constants all the time. And the usual convention is early letters of the alphabet are constants, right? A, B, C, D. And later letters of the alphabet, X, Y, Z, W, tend to be for variables, right? Now, let's do a differentiation, a partial derivative with respect to X. That's a quotient rule. So it's going to be f dash g, take away f of g dashed over g squared. Put little brackets around. If you differentiate the top with respect to x, don't you just get a? Ax, differentiation, a. What about the by? It's a number. Derivatives of numbers don't get you anything. Times g, which is this guy. Take away. Leave the top one alone. What do you get when you differentiate the bottom with respect to x? Yeah. All over cx plus dy squared. And you know I'm not leaving that, right? Style points kicks in. If you distribute through, you get acx plus cdy, take away acx, take away bcy. All over cx plus dy squared. And sometimes you get lucky. Do you see those two things cancelling each other out? And right now I'm left with cdy, take away bcy, all over cx plus dy. And we might be finished. And I can imagine a lot of situations where we would be, but not this time. Is there anything you can do to the top that makes it a little bit prettier?
Professor, you have CDY for your first value, and it should be ADY. You distribute it as a C instead of an A to.
I gotcha. Right. Thank you for catching that. It's an A. Actually, it's an nice easy fix. It would have been worse if it had been something else, right? ADY. Now, is there anything on the top that you can do to make it pretty?
You can factor out a y.
Just because I'm looking at it right now. If you get a very special situation, but can you imagine the AD take away BC is 0? Can you imagine certain combinations of A, B, C, and D that would be true, right? Can you imagine that happened? If that was the case, wouldn't this partial derivative be 0? I have no idea what that's telling me, In general, would you agree that this is representing every linear fraction in the universe? Every linear combination of x's and y's top and bottom. So evidently there is a subgroup of linear functions whose derivative will be 0 all the time, no matter what x or value. God in Himmel, what would that look like? As you slice it parallel to the x-axis, it's always a hill. I have no idea what that would look like. It must be weird. So let's move on to multiple derivatives. In Calc 1, you might have a function looking like that. Okay. And if you differentiate it with respect to x, you would get 4x. Great. And I could also call that f dash, but I'm not going to do that notation. Now, couldn't you differentiate it again? And when you differentiate it again, isn't it called the second derivative, right? So this is called very often the first derivative. And if you differentiate this, you get the second derivative. And what would that get me? 6x plus 4 in this case. The notation for the second derivative is a bit wonky. Don't think we've actually focused on it. But do you notice that the 2 goes in a different place? It's between the d and the y, and it's after the x. If you want to just be, why do they write it that way? Why don't they just call it, I don't know, why don't they just call it that? You know, that kind of thing. Why is that not the notation for the second derivative? Why is the 2 here and the x is there? It comes from this. The second derivative is actually the derivative of the first derivative. Great. Now, do you see the dx's are the same? So basically, don't you get a dx squared? Aren't the d's the same? Don't you get a d squared y? I don't know if that helps or not. Otherwise, will you just say, okay, that's how you write it, I'll live with it. So we are going to now do second and third and as many derivatives as you could possibly want of a function. So I'm going to begin with this guy. And I'm going to find his partial derivative with respect to x. And his partial derivative with respect to x would be 3x squared. What would you get if you differentiated x squared y to the 4 with respect to x? What would this guy get you? Any takers?
Y to the 4.
Assuming I heard a 2 there, probably did. Great. Now, if I wanted to do the second derivative, do you see I would use that same wonky notation I was talking about a minute ago, right? That means find the second derivative. Wouldn't it also mean find the second derivative again with respect to x? So that's pretty obvious, it is x, right? In this case. So you would get 6x. What would you get when you differentiate this guy with respect to x?
2y to the 4th.
Just because you can, although they don't typically go very often more than the second, but you know, just in case they do. The third derivative, wouldn't you just get 6? Right? Differentiating 6x, you get 6. What would the 2y to the 4 get you? If you differentiate 2y to the 4 with respect to x, what would you get out of that?
0.
0, right? And just because I want to, can you see in this case then, you know, after the fourth derivative, wouldn't all the answers be 0, right? But, you know, that's just a particular situation. Does second derivative seem pretty much Calc 1-ish, right? You just do partial derivatives instead of full derivatives, for want of a name, right? I should do it over here. But I'll do it in red. Let's start and do the partial derivative with respect to y. Well, that'll get me nothing. This guy will get me 4x cubed y cubed, and this guy will get me 3. If I do the second partial derivative with respect to y, this guy gets me 12x squared y squared plus nothing. If I do the third one with respect to y, I get 24x squared y. If I do this one with respect to y, I would get 24x squared. And then can I keep, well, I wouldn't need to go much further, because wouldn't the next answer, if I did it to that's a 4. If I did it to 5, I would get 0, and 0 forever. Would you agree it's not a surprise that these answers are different, right? Differentiating with x, you don't normally get the same answer if you differentiate with y. Agree? That's kind of par for the course. I want to introduce you to some notation. This one we know, right? Can't you call it just z little x? If you want to do the second derivative, we could call it z double x, right? Just for completeness sake, if I wanted to do it with the y's, it would be called z double y. And if I wanted to do it a single guy, it would be called zy. Right? No biggie, right? Would you agree that makes perfect sense, right? So if someone said to you, I wanted z x x x, wouldn't you realize that was a third derivative with x's? Okay. Now something weird is going to happen. And it is weird. And it's also true. This is a thing that you will be asked to do. I'm going to pick a new function. And it's going to be...
Can I see that notation paper again, please?
Sure.
Thank you so much.
Yeah. Suppose I have e to the x plus y cubed x squared plus 4. Right? I'm going to start with nothing really surprising. I'm going to differentiate this thing with respect to x. So again, e to the x plus a 2y cubed x. Nothing weird at all about that. And I'm going to also do it with respect to y. And that gets me nothing, and that gets me nothing, but this guy here gets me 3y squared x squared. So far, so good. You might think I'm now about to do a second derivative with x and a second derivative with y, but no. In fact, I'm going to call this guy zx. I am going to do that guy. This is the weird stuff. What on earth does this mean? Well, it means I am going to find the partial derivative with respect to y of that guy. So here is the partial derivative with respect to x. I'm now going to find the partial derivative with respect to y. Do you see that you're allowed to change who you call the variable every time you differentiate? Seems a bit weird, but you're allowed to do it. Now, if I differentiate this expression with respect to y, what do I get? Well, that gets me nothing, and this guy gets me 6y squared x. Are you comfortable with that guy getting me this? Okay, what about this fella? Well, suppose I went and asked you to do that guy. Wouldn't that mean differentiate with respect to y first, and then whatever the answer is, differentiate it now with respect to x? So we are going to differentiate this guy with respect to x. And if you differentiate this guy with respect to x, you get 6y squared x. Do you notice anything about those two answers? It's pretty obvious, isn't it? Now, was that just a sheer coincidence? Because sometimes coincidences happen, right? You might think, oh, it's just a coincidence, because sometimes, pretty rare, but haven't we had done questions where these two guys were the same? But that was more coincidence than anything, right? These two guys, that's not a coincidence. There is a French guy called Claire O. How do you spell Claire O? I think you spell it with a French A-U-X. Claire O is his name. And he figured out that second partial derivatives, if you use the same two but in different orders, right? You do x then y or y then x. He figured out that they're always equal, provided the original function z is continuous. So that basically means nothing's weird, right? It's a nice surface, right? A nice, surface of a sphere or whatever it might be, right? And that's a very interesting result, because if you give me a question where you ask me to get both of these, won't I just find this answer and then just write the same one down for the other one, provided I know the function's continuous? Secondly, couldn't I use that as a proof that a function was continuous? Couldn't I find this answer and then find that answer and say, hey, they're the same answer? What does that tell me? It tells me the original function is continuous. So what does things that are not continuous look like? Can you imagine this as a surface? Can you imagine there's vertical asymptote? Would you agree it's not very continuous at the vertical asymptote? That would be an example. Can you imagine a function which had a curved shape going like this, and then a space and another curved shape like that? The equivalent of what, I guess, a piecewise function. Can you imagine surfaces where they don't meet? Would you agree that's not continuous? There's a problem at the seam. In those situations, that will not be true. And it won't be true, at least close to here, because of that guy giving a problem or that guy giving a problem. Now, that's not all that Clairaut figured out. He figured out this, which I think is even more weird. I have just written down a fifth derivative. I'm going to do a partial derivative with x. Then that answer, I'm going to differentiate it with y. Then I'm going to differentiate it with x. Then I'm going to differentiate it with y. And then finally, I'm going to differentiate with y. Do you see the order I'm going to do it? He figured out that it's the same thing as that one. Now, you know, when you do differentiation with x's as a variable or with y as a variable, don't things disappear and get treated quite differently in lots of situations? Yeah, that is true. Which means that any order you like will work. Couldn't I do all the y's first and then finish with two x's? I could do all the x's first and finish with all the y's. Why is that useful? If you're doing multiple partial derivatives and you're being asked to do a certain calculation, sometimes you should pick a particular order to make life easy. I'll give you an example. Suppose I had a function that looked like this. Suppose I had that function and you asked me to find that partial derivative. Now, wouldn't I have to, if I did it in this order, wouldn't I have to do the x's first? Would you agree doing the x's here would be absolutely horrendous amount of work? On the other hand, since it's equal to this guy, wouldn't that be relatively easy to do? Because I would do the y first and then I'd do the x. Well, I should be able to do that. If you differentiate this with respect to y, doesn't all of that get you a big fat 0? Right? Differentiate with respect to y, that's 0. Differentiate that with respect to y and you get 2yx. Now, take that answer and differentiate with x. Boom. Do you see how easy that calculation was? Because I chose to change the order of differentiation, right? I choose which variables to do first, second, third. And as long as I use the right combination, right, it's going to be equal to each other. Oh, come on, is that not fascinating? That you're dealing with partial derivatives, you can be in charge of the order. If you think one order is going to be easier to do than the other, then do it, right? So if somebody gives you this guy and asks for this fella, I hope you all do that. Now, if you're just one of those robots who, if you give me it that way and you tell me that, I'm going to do x's first and then I'm going to do y's, well, good luck to you, right? And I'll see you in 2 hours when you're finished, right? Pretty cool. Now, there is a really annoying notation problem, so let's just get that out of the way. I love that notation. To me, it's easy to understand, right? X is first, Y second. Great. X is first, Y second. This notation, no good. Do you notice that the X's and Y's are in a different order? If you want to write this guy using the delta notation, it's clunky and it's kind of, in my mind, back to front. Give you another example of this ugly notation. This is ugly. If I said to you x, y, y, just for argument's sake, it's a third derivative. That top part's not bad. The bottom part is a problem. Would you agree this notation is very clunky, right? It's kind of hard to figure out what you're being asked to do. But you are actually being asked to do it in that order. And I just screwed that up, didn't I? Which is another reason why I hate that notation. There. X is Y and Y. You know, reverse. Are we good? Suppose I had that one. X or Y, where my finger is. What goes here?
X.
It's not a biggie. Maybe I'm making more of it than there is. But would you agree that when you see this notation, you just have to be a little bit more careful? And you might say, well, Clairaut says that they're both the same, right? As long as you do them in one math. But didn't Clairaut also say only if it's continuous? Not every function in the universe is continuous, right? Can you imagine there's some ugly vertical asymptotes and weird stuff going on? In those situations, it's not true. Matthew, what's your question?
On the second one you did, can it be written as dy squared dx at the bottom, or not?
Oh.
Not d, like the.
Yes, it can.
Okay, I was just double checking that. All right, thank you.
I don't think it helps the notation much. We just agree it's still downright ugly, right? But you know, like everything, do you know when you did Calc 1, wasn't f dash or y dash good notation, and wasn't dy by dx really clunky? But didn't you need dy by dx when you did change a variable and some other stuff? Wasn't that notation helpful in those questions? Agreed? So I'm not going to say that that is a hopeless notation. It's useful in niche markets, right? Like that is a useful notation when you're doing certain things, right? So it does need to be, you need to be aware of it, right? Because you're going to use it. I think we have learned some really cool stuff today. We should finish with a joke. Has anybody got one? While I'm thinking about it, you say your last name. Anybody got a joke? Did I tell you the joke about the Scotsman going to the Highlands of Scotland? Or I should say the American going to the Highlands of Scotland. Okay. I did tell you that one?
The happy hour.
Yes, I did tell you that one. Happy hour one. Okay, then I'm not telling you that joke. I told that to one of my other classes. My Calc 4 students thought it was funny. And my trig class, it was a dead. I think you lot, it must have been a dead end because you didn't even remember I told you it. So that's how memorable that joke was. Okay, here we pick on. Did I tell you the one about the fire, the oil fire? So in Texas, there was a big oil rig fire, and the owner got on the phone and he was talking to all the companies that do that. You know, get a big oil fire, I'm losing lots of money, I've got to put this fire out. And all the companies were busy. And when he phoned the last company, he got desperate. He says, look, I'll take anybody. I don't care how bad they are. It's better than nothing. Do you have any ideas of a company I could use that's not busy? And so the guy says, well, there's one company, it's a Scottish company. He says, they're really useless. He says, they're just startups, they get nothing. But I'll give you the name. So he phones the guy up and the Scots guy says, not a problem, we'll turn up tomorrow. And so the owner is waiting at the bottom of a hill and the big oil rig fire is right a little way away. And he looks up and he sees this old battered truck with about 20 guys in the back with shovels and brooms. And it comes down the hill and he thinks, oh, that's interesting. And instead of stopping, they just got faster and faster. And by the time they hit the bottom of the hill, they're doing about 80 miles an hour. And they zoom right by the oil guy and they crash into the oil rig, the big well. Knock the top right off. The guys in the back jump out and they were batting their flames out with their hands and they were beating the fire with their shovels and their brooms and throwing something in. 30 seconds later, the fire's out. And the oil rig guy's amazed at this. And so the Scots guy goes over and he signs on the check and he hands him the money. He says, I've never seen people put a fire out like that before. That was amazing. He says, what are you going to do with the money? And the guy says, well, the first thing I'm going to do is get brakes for that bloody truck. Okay, I think you've suffered enough. Have a nice day, everybody. I'll hang about for any questions. Bye-bye. Bye-bye, Eli. Eli. Okay. Dylan, Christopher, or Eric, any questions?
No, I have one. It's
What have you got?
on the last one was the e to the sine x. Well, no, I guess not the last one, but the last problem we did. I just wanted to know when you were moving x and y across the equal sign, how you balanced that. Just because I seem to have lost a step. I don't know if I just wrote it down incorrectly.
I'm not sure where my question is that had that one. Can't see it. Did I throw it away? Who knows? Let's check. So what does it look like again? It
Z equals x squared e to the sine x.
Okay, let me just write that down. That's easy enough to recover.
Okay.
Put that over here. I need another desk. I need a bigger desk. Right, so Z equals.
X squared e to the sine x.
Okay, that's oh, that really ugly one, right? It doesn't. Yeah, it doesn't quite matter what I put in here. So even if this is not the same thing, it really doesn't matter.
Yeah, so I mean later on the part that I had the problem with was z subscript x y equals z subscript yx. And then
Okay.
you manipulated that.
Right. Clairaut says that if this function is continuous, which I'm assuming that it is, that if you want to get this second partial derivative, this one here is the same thing. And so instead of doing x first, and then once you got that answer differentiating with respect to y, which is what this is saying, do x first and then y. That would involve an awful lot of work because differentiating that would be horrendous. Would you agree? That's just not a good thing to differentiate, right? So what we suggest is, or Clairaut says, look, you can do that one. So you do y first, and then whatever that answer is, differentiate it with respect to x. Well, if you differentiate this with respect to y, since all of this is constant, its derivative is just 0. And if you differentiate this with respect to y, you just get x squared. So that guy is just x squared. And then differentiate the answer with respect to x, and now you have got 2x. And what that has allowed us to do is to find this second partial derivative really quickly.
I see that makes a lot of sense.
Right. So that's what we did.
Thank you.
You're welcome. Eric, you got a question for me?
Yeah, I have a question. It was on the one where we input the value. It was
okay.
The derivative
with a whole load of stuff and a pie in it. That one?
No, I think it's the one where it's t times e to the s divided by t.
Okay, so t times e to the
s divided by t.
Ooh, that's ugly. Okay.
And it's the derivative with respect to t 0, 3.
Okay, so I'm going to differentiate this guy with respect to t first. It's a product rule.
Yeah, that's what I came up with. I came up with 6yt. Oh, sorry. The first one was e to the x plus 2y.
You're going to have, you're going to have e to the s over t 1 times it, but that's what that is, plus t differentiate e to the s over t, you get e to the s over t times that guy's derivative, which is this guy. So you will get e to the s over t. That's this one. That's a negative. One of them will cancel. So you'll get negative s over t e to the s over t. So that's what I get for the partial derivative with respect to t. Do you agree?
Mhm.
Okay, now you want to do it. This guy here is going to be called s, and this guy here is going to be called t. And why? Well, alphabetical order, you know, like X, Y, Z. So S, T, R, S, T. So I'm going to get e to the 0 over 3, take away 0 over 3, e to the 0 over 3. Well, e to the 0 gets you 1, and that gets you nothing. So the final answer would be 1.
Oh, okay.